All right, in the second video, I'm going to talk about sets. So that is a section 2.2. So we defined variable as the one that takes on different values, and we may collect all of the possible values that the variable of our interest can take on and describe in terms of set. Okay, so here is one example. Say variable x can take on one of the three numbers 2, 3, 4. Then we label capital X as a set. So the collection of possible values. So it collects a 2, 3, 4. Okay, and then we use a curly parenthesis when describing a set. Okay, so this means X has a three elements 2, 3, 4. And then right, because X can take on one of these values. So X is a variable X, small x is an element of set capital X. Okay, so this notation means X is an element of the set X. Okay, so here variable X can take a distinct values, one of a 2, 3, 4. But some variables can take any number between 2 and 5. Then we can write so we can write this in terms of set as so this set is the set of y such that y is a real number between 2 and 5. Okay, or in a more simple way, we can write like this. So y is an element of, okay, any number between, so y is an element, so y is any number between 2 and 5. Okay, so this notation, once again, it means it belongs to, and then 2 and 5. Now I take a bracket, okay, that denotes a interval in mathematics. Okay, so when we express a interval, we use a bracket or parenthesis. Okay, so this parenthesis means this is an interval between 2 and 5, but the boundary points 2 and 5 are not included in the set. So this means y, so y can be any number between 2 and 5, but y is strictly larger than 2 and strictly less than 5. Okay, so the boundary point is not included in the set. And then with a bracket, we mean by the bracket the boundary points now are elements of this set. Okay, so y is larger than equal to, y is a larger than or equal to 2, but a less than or equal to 5. Okay, and we can think of a 2 and 5, another interval. Okay, so to 2, I attach a bracket, but to 5, I attach a open parenthesis. That means now if y is an element of this set, that means y is any number larger than or equal to 2, but strictly less than 5. Okay, so we can use we can express a set in words like this, or using math symbols, we can express this way as well. Okay? We can express this this way as well. All right. So a set is a collection of possible values that one variable can take on. All right. But in general, we can define set as a collection of different objects. All right. So here objects can be anything. It can be possible values of one variable, but it is a set may denote a collection of any different objects. Okay. So here object can be some another set. So we can think of a set of different sets. For example, we have two different sets right here. So the first set is a collection of odd numbers, larger than 1 and but less than 5. And the second set collects even numbers between 2 and 6. So 1 3 5 and 2 4 6. And then we can think of a collection of these two sets, okay, by adding another curly bracket outside, okay, that can be defined as another set X, okay. So this is a set of sets, right, simply. So this concept is used in economics, especially when describing an information structure. So this information structure doesn't appear on the textbook, but it's not that difficult. It's not that difficult to understand. So let me explain here. Suppose that you cast a dice, okay, and you are informed of whether the face is a odd number or even number, okay. In this case, your information structure, so what you know, takes the same form as this, okay. So we have a different sets inside. This means you can distinguish these two. So if a dice is cast and the face value, so the value on the upper surface turns out to be 2, then you know that because this is an even number, then this event does not happen. Okay? So this event happens, but you can't distinguish between these three numbers. So you don't know whether that is a face, so whether that face value is 2 or 4 or 6. But this event, so 2 4 6, one of the 2 4 6 does appear on the upper surface. Okay? That is an information structure, right? So each element of the structure is called the information set, and the way to interpret this set is if one of the event of information set 135 information set is an element of information structure. So information structure means this set X in this example, and 135 is an information set. Okay. So if one event of information set 135 happens, then some event in the set happens, but you can tell which event indeed it does. Okay? Suppose a face value is a 1, then this event happens, so the face value is an odd number, but you can tell which odd number. Okay, that's the way to describe this information structure in economics. So the set of sets can be, we can imagine a set of sets, and that is applied to economics as well. All right, and in the second slide, let me explain relations between sets. Okay, so given two sets A and B, we say A is a subset of B, and we write this way. So that is read A. So set B includes all elements in set A. Okay, so simply B includes A. In other words, A is a subset of B. Okay, so if every element of A is also an element of set B. Okay, so the way to express this, another way to express this is if A is an element of set A. Okay, so this implies element A has to be an element of set B. Okay, then we say if this holds, then this statement is true, then we say A is a subset of B. Okay, and if A is a subset of B, then we call set B as a superset. So this is equivalent to saying set B is a superset of set A. Okay, superset. Okay. All right. So this is a opposing notion of opposing notion to superset or subset. Okay. And A is then the second bullet point. A is a proper subset of B, then here, if we simply say A is a subset of B, then the notation, if we take a look at the notation symbol, then we have another bar here. Okay, so that leaves a possibility two sets are exactly identical. Then, but if we express A is a strict subset of B, or we say proper subset of B, that means it rules out possibility that two sets are identical. So B strictly includes set A. Okay, I think it's better to show you a figure. So if this is a set B, and the set A is a included, totally included in set B this way, then A is a strict subset or proper subset of set B. Okay, then we rule out this a bar from the symbol. It means if A is an element of set A, then set element A should be has to be an element of set B as well, but not vice versa. Okay. So the first statement allows the other way as well. Then set A and B are equal to each other. Okay, that is a third bullet point. So two sets are identical, and we write A equals B, and that is true if A is a subset of B and B is a subset of A. Okay. And two sets are disjoint or mutually exclusive. That means two sets have no common elements, like this is set A and this is set B. Okay, there is no common area, meaning that there is no common elements, between these two sets. Then we say two sets are disjoint or mutually exclusive. Okay. So here is one example. Set A is a collection of a 135. B is a collection of a 13579, and clearly A is a proper subset of B. Okay, so we may write A is proper subset of B, or A is just a subset of B. Okay, these two statements are true. And if a set has n elements, then there exist 2 to the power n possible subsets in total, including the empty set, this null empty set. So that means if I take an example, say we have a set A 135 and how many subsets this set A have? If we think about this question, so how many subsets does a set A have? Then this set A, we can think of a possible subset of a set A. So empty set. So first a set 1 is a subset of A, and 1 and 2 is also a subset of A, and now 1, 3, and 1 and 5, and 3 and 5, and 1, 2, 3, and 5. Okay, so 1, 2, 3, 4, 5, 6, and what else? 3 and 5, 1, 5, and 1, 3, 5, the entire set. The entire set can be thought of as a subset of A, and we count empty set as a possible subset of any sets. Okay, so we can write a empty set. So this set has a no element, but this is a subset of A. Okay, any set. So we count empty set as a possible subset. So the empty set is a subset of every set. Okay, so this statement is true as well. Empty set is a subset of empty set. Okay, but this statement is not true. Empty set is a proper subset of empty set because these two sets are identical and having no elements, right? And how to operate sets. So we're going to study four basic operations. First, the union of two sets. So the union of A and B is defined as the set of which the set which contains all elements belonging to set A or to set B. Okay. So formally, A union B is a set of elements X. So X such that X is a element of A or element of B. Okay. So if we have two sets A and B, so A is a 3, 5, 7, B is a 2, 3, 4, 8, then the union of these two sets will be, this is pretty easy, right? So 2, 3, 4, 5, 7, 8. Okay, so the collection of every element in set A or set B. Okay, so 3, 5, 7 is right here, and the elements of B are 2, 3, 4, 8 is right here. So A and B collects all elements in both sets. That is the union. All right. So using Venn diagram, the union of A and B can be depicted this way. So this is set A, and this is set B, and the union of these two sets will be the entire area. Okay. So another way to define union, so another way to see this union is this shaded area includes a set A and also includes set B, right? So A union B includes a set A and includes set B, right? Okay, and that is the smallest set. Okay, so for example, we can think of this set as well. Let me call this C. C also includes set A and includes set B. Okay, includes both sets. But the union of A and B is the smallest set, including both sets. Okay, so the another way to define union is this is a right. This is the smallest set, including A and B. Right? There are plenty of other sets, including set A and B, but the union A and B is the unique set, the smallest set, including both. All right. So this is the concept union of two sets, and then we can think of an intersection. So intersection is the set which contains all common elements. Okay, all common elements. So, so union is defined as a collection of elements such that X is an element A or X is an element of set B. But for intersection, then we may use AND, okay? Because it's a set of all common elements. So the element of the intersection must be element of set A and element of set B. Okay. So this is a definition, mathematical definition of intersection. So if we have a set A, -3, 6, and 10, and the set B as a 9, 2, 7, or 4, then intersection of A and B, because there is a no common element, right, is going to be empty set. All right, and just as we define the union in an alternative way, we can define intersection as so here is the diagram displaying the intersection of A and B. Okay, so here the shaded area is a subset of A, also subset of B. Okay, so let me write this. Okay, so A intersection B is included in set A and included in set B, right? And that is a large set having this property. Okay, so we can think of another set, say, right here. So this pink set is also included in set A and included in set B. Okay, but the intersection of two sets is a largest set contained in both sets. Okay, so we can define the intersection as the largest set included in both. All right. Cool. And the third operation is complement. Complement can be it is denoted by a tilde or AC. Here C is for complement. Okay. So equivalently. So in the textbook uses a tilde, but in this course, let me use a super C to represent complement of set A, because that is much easier to type. I have to make these lecture slides, but it takes forever. So to save my time, let me use this notation instead of this. Okay, these are exactly equivalent notations. So anyway, the complement of set A is the set which contains all elements not in A. Okay, so in order to define this complement, we have to define the universal set. So imagine that this rectangle represents the universal set. Okay, and we are thinking of a subset of this universal set. So set A is a subset of this rectangle universal set. All right. Then the complement of A is the collection of all elements not in A. Okay, so this is a shaded area. Okay, except a set A. Right, that is the complement. And finally, we can define difference between two sets. Okay, so the difference can be expressed as a minus b, just as we express the difference of two numbers as a minus b. But to distinguish this is to distinguish set difference from the standard difference. Sometimes we use this backslash. These two have the same meaning. The difference of A and B, difference of two sets A and B. So the difference is defined as the set of all elements in A. So in A, but not in B. Okay. So formally, we can write A minus B as the set of elements X such that X belongs to set A, but X is not an element set B. Okay. All right. So from this definition, let me first show you a graph. So here is set A. Suppose we have set A, and we have set B here. Then A minus B is a set of elements X such that X is a element of set A, but not an element of set B, right? So this is going to be this region, okay? This region. All right, so shaded region collects all the elements in A but not in B, right? Okay, so going back to slides, Okay, so X is an element of A but not in B. So how can you write this using set operations? So we know and is an intersection. Going back to the definition of intersection, A intersection A and B is a X is an element of A and X is an element of B. Okay, so the only difference is for set difference, we have this bar. So this bar means X is not an element of set B. So that is a complement. So we can write this as A intersection B's complement. Okay, because the intersection is and we have a rule that is X has to be element of A and X is not an element of B, that is a B's complement. So the set of the difference of two sets is a intersection of set A and the complement of set B. All right, then there are some laws of these operations. First, a commutative law. Commutative law means we can change the order. So the union A union B is the same as B union A. Okay. Similarly, A intersection B is the same as B intersection A. Okay. So we can change the order whatever we want, and the associative law. So we have here two unions. So A union, B union, and C. Okay. Then we take the parenthesis first, B union C. Then we can move this parenthesis. So then this parenthesis means we first take the union B and C. Okay, and then take the union with A. All right. Then we can change the order. We first take the union on A and B, and then take a union with C. And then the results are the same, okay? Because we have only unions here, okay? On the left and on the right. Then the which set we have to take the union first, it does not matter. Similarly, we have intersections only here and here, okay? Then does not matter whether we take the intersection A and B first or take the intersection on B and C first, okay? Results are the same. And the third law is a distributive law. So here we have a union B intersection C. So here we first take an intersection on B and C, and then we take the union with set A. Okay, so we have both operations, union and intersection. Okay, then we have to distribute this union. Okay, just as if we have A times B plus C. Okay, then if we first do addition of a B and C and then multiply by number A, then usually we distribute this constant A in the parentheses. So that is A times B plus C times A times C, right? And so similarly, we can distribute union through the parentheses. So this is the same as A union B. intersection A union C. Okay, and here we just interchange the order. So we first take the union on B and C, on B and C. Okay, B and C. Where is the other component? This is a typo. All right. So now we take the we distribute this intersection in the parenthesis through the parenthesis. Then B becomes A intersection B, and we have a union in the middle. Distribute A to C, then C becomes A intersection C. Okay, that is a distributive law. And finally, we have a De Morgan's law, or not De Morgan, it's De Morgan. De Morgan. So okay, so De Morgan's law helps us distribute complement. So if we think about the complement of union of A and B, okay, we have this, and the way to distribute complement is first we take complement on each set. So A becomes a complement, B becomes a B's complement. Now we have to change this union to intersection. So the union's intersection becomes union's complement becomes a intersection, and then intersection's complement, and vice versa. Intersection's complement becomes a union. So the complement of the union of A and B is now A becomes A's complement, B becomes a B's complement, and the intersection becomes a union. So we have this. That is De Morgan's law. Okay. So I think knowing these four laws is enough for is enough for us. So now let me do one exercise here. So yeah, let me do just the first one, and I'll leave the other three for exercises. So prove or disapprove the following statements. So now think about a first one. So this is a set difference, the intersection of B and C. Now we are asked to prove whether this is true or not. So that is equal to A minus B union A minus C. Now using a set operations, first so how to prove this? Okay. Because A minus B intersection C, first using definition of set difference, we can write this as A intersection the complement of the second element, because A minus B was a intersection B's complement, right? So the minus set difference between A and B intersection C should be this, right? Okay. Now we use a De Morgan's law to distribute this complement notion. So A intersection. So now B becomes a B's complement, and the intersection becomes a union, and C becomes C's complement. Okay. Now using the distributive law, let me distribute a intersection. Okay. Then B's complement becomes A intersection B's complement, and union C's complement becomes A intersection C's complement, right? And finally, once again, using the definition of the set difference, A intersection B's complement is A minus B, and union A intersection C's complement is A minus C. So we just proved the first statement. Okay. All right. So this is the second video. In this video, we define the sets, and we also briefly discussed how this applies to economics using the information structure example. And then we studied relations between two sets, subset, identical sets, and proper subset, superset, and the mutually disjoint sets. And we also studied several operations, union, intersection, complement, and what is the final one? Yeah, set difference. And we also studied how to operate. So these are several laws of operations, right? So thanks for watching. And then the final video will be available soon.